What I'm going to talk to you today about, as if you've, is ADAS and automotive driving for the trends. I'm going to talk a little bit about best practices that we're doing for ISO 26262 safety. We're going to go then and roll into those features that are put in all of the IP that we provide, and then talk a little bit about automotive reliability and quality. After seeing some of the other presentations, a lot of people have read the National Transportation Board report, which goes into some incredible statistics, which is quite shocking for all of the automotive, and talking about automotive accidents. And again, so with 6.2 million of them, that's a whole lot of that, whole lot of deaths too. I mean, you might as well, drink and smoke and enjoy your life rather than getting hit by a car. But the thing is that a lot of those are preventable. 94% are human error. This is about people. A lot of them are on their phone, and a lot of them are texting. A lot of them are distracted. A lot of them might be sleepy. Some of them might be DUI, but it happens a whole lot. But out of all of those things by human error, the other 6%, 2% are the environment. Rain, snow, bad visibility in a dust storm, mechanical, something that actually broke, flat tire, and somebody goes off that, and 2% margin error on the study. So I think we are our own worst enemy when it comes to that, and driving on the freeway can be a dangerous thing. So what are we going to do about it? What we're going to do is we're going to load up our cars with cameras. We put cameras in automobiles. Now again, the simple one is the rear view camera. How many people have backed into a pole? Yeah, okay. The rest of you, it's okay. We still respect you. We just understand you don't want to do it in front of this large audience here. I just did it about 6 months ago. Good thing my son's a mechanic and we could do it together. Front camera, pedestrian detection. This is really, really, really key in terms of the front camera being able to take when somebody walks out in front of you. Can the software detect the difference between a baby carriage, a fire hydrant, a shopping cart? All of these things, it has to be able to do that in real time. And now the real danger comes is when it's one thing to have these cameras on there, they're watching things, they're detecting things, but when you talk about automatic emergency braking, that system, it's a closed system, and that car is going to do something that you didn't necessarily plan. It's going to stop suddenly. What about the guy who's riding your tail? Exactly. So you have to be real careful, and so you have to use that rear camera to say, should I really hit the brake that hard, or is this clown going to plow into me? And then the surround view cameras. There's some great pictures over here about how the cameras, you're looking for traffic signal, you're looking over here, you got right in front, you got surround view, and so you're looking at all these cameras, and what does that make? It makes a lot of data, a lot of video to process, and that's going to be one of the things that's even outside the car. But not only is it outside the car, it's inside the car. This drowsiness, gaze detection, they can tell when you're looking at your phone, and so cars will be saying, hey, stupid, quit looking at your phone. I know you're doing that. And this is going to help keep us safe, because I believe that's where most of those real problems are coming from. And so we have, long-range radar, LiDAR using, lasers. There's cameras, and then there's ultrasound, which is the typical backup camera that, the backup signal that'll beep. So we have all these things. All this data is coming in and needs to be processed. And what is it going to need? It's going to need sensor interfaces and a whole bunch of processing power. So first of all, for the sensors, we got all those sensors in there. All of that data got to be crunched. It's got to be processed. We're seeing some 64 bits with co-processors in order to offload the data. Embedded vision processors. This is the key thing. Being able to learn, oh, that is a stop sign. Oh, that's oncoming traffic. Oh, that stuff, that's the white line you're not supposed to cross. those are the bumps on the side of the road that says you're on the, you're on the side of the road. And so basically being able to learn these things and learn it not necessarily something that can be pre-programmed, but when the car is on the road, being able to pick up these things dynamically. Hey, it's raining. Things are going to be different. And being able to do that, and then the vision algorithms and, convoluted neural networks, and being able to have ways to be able to learn, to be able to adapt as it's going on. And so that deep learning is a lot of software, a lot of memory, and a lot of processor. And now what we have to do is we have to connect all this stuff. The car cable harnesses are getting really big. So you want to carry an extra 500 pounds of copper, you're going to lose about 5 miles per gallon just with all the copper that you're carrying there. So what's happened is that stuff is all going out. And so you were talking about Ethernet, going to be rising it. It's good cables, between, for the, but again, this stuff has to be fast. It's not just a regular electric signal. You got to process it, you got to serialize it, you got to encode it, you got to decode it, and it's got to come back. And it's also time sensitive. So it's okay if that signal comes back, but 5 minutes later after you passed your turn, that's not going to happen. So we have that. These things are going to need a ton of memory. DDR memory. So what does that say? LPDDR. They're going to be special camera interfaces. So a lot of people are using MIPI. MIPI is really taking over on the cameras, and then even the I3C, which is yet another sensor interface that comes to that. PCIe to get to the bus. USB inside there, because now even the smallest Chevy is saying, oh, you can have your own hotspot, and be your USB, so everybody in the car can look at their phones, except for the person who's driving. Yes. And then Bluetooth again, because you have your heart monitor on, so you can, if you're driving with a teenager, which is really important. And so, 5G that. And we have advanced process nodes. Now, in order to put together a 64-bit processor, watching half a dozen, or a dozen cameras, you're going to need a lot of processing power. So what does that mean? It means putting it on advanced nodes, 16, 14, 10, 7 nanometer. You're going to have to put it on those advanced nodes because you're going to have to do a lot of processing. And what is it, why does it need all the logic? GPUs. So you might have 10, 15% of the chip is the CPU, but it's those GPUs, those dozen of those, and as the more embedded vision you have, the more GPUs, because they can process these things in parallel, and that's what's going to be taking up the space. And also, now that we have this thing applying the brakes or doing corrective steering, when you go over the line, safety is what's absolutely critical. And as you can see here, it's growing, and there's going to be a lot more semiconductor revenue. And what does that mean? That means your paychecks. Because you guys are making silicon and systems. So it's a good idea to see where that's coming from. So there's a couple different kinds of SoCs. Over here, we got our big high end. Okay, this is a thing watching a half a dozen cameras, and what it's uniquely coded is for those things that are in the purple are stuff that Synopsys has. The gray things are the things that Synopsys doesn't have. You can see we cover a whole lot of that, especially on the high end, from CPUs to DDR controllers to even the basics that are coming in there, logic libraries, embedded memories, and data path. And so this is the big one. This is the one everybody's swinging for. Okay, this is the one all the cool people are designing that one. There's a few of those that are going out, and there's from some of the big companies. There's a lot in infotainment. In order to basically hook up with your phone, run the screens, run the maps, run other things, there's a processor. Doesn't quite need all of that horsepower. A lot more multimedia, a lot more camera processing that goes in there. And those are not necessarily in the most advanced node. But the real workhorse of the automotive industry is these guys, MCUs. My son happens to be work for BMW, and there's, on a typical car, there's 100 of these things. They got one on each wheel to run the ABS. They got them in the engine. They got them in the control. They got them in in the doors, it's on the blinkers, it's on the lights. I really like the ones where the light turns as you're turning right, and you can see that spot. I mean, there's good stuff. There's processors in there. 8 bangers, 16 bangers, 32 bangers, and again, on all of these different chips, and there's a lot of these. The one thing that you're going to see in here that you haven't seen before, this one here, security. How many people have seen that video where the guy's driving along in his laptop and he takes over the car that's driving next to him? I think security is going to be important. So, what are the best practices for this functional safety? From both things that can go wrong as well as bad people who want to do things. So, ISO 26262. This is a way of thinking, a way of being really dull, being really boring, and being the adult in the room. And so there's hazardous impact. And so what the system does, they divide it into 4 categories: ASIL A, B, C, and D, various levels of safety, depending upon how critical something is. If your radio's not playing, okay, you have to sing. However, if there's something in the braking system, steering system, that's real big time. And so the goal is to, minimize it. What are the requirements? Develop it. What can go wrong? How can you mitigate what's going wrong? How can you detect it? How can you prevent it? There's a whole bunch of training. There's some people we go work with. These guys, SGS2, the Germans have been doing this for a while. And they go through, and there's training, and just taking the design team and saying, this is the system. They appoint somebody who's the safety manager, who is, it's a drawing the short straw. It's a tough job. Are there any safety managers here? Okay. So the best practices, they have a FMEDA. So what is the failure mode, and where is it, and how are we going to detect it? First thing it does, it's reviewed by multiple engineers to eliminate bias. Because everybody says there's nothing wrong with my circuit. No, my circuit's fine. I've thought through it. What about? Okay, so you get a team together, quality circles and those kind of things, puts together a cooperative thing. How are we going to make this thing really safe? There's a safety manager who's the adult in the room. We have review key documents. There's a block-by-block analysis, because each block could affect something else, could have a different failure mode. And basically ending up with gate count numbers. And now again, for the part of this system that I do, I work on basic logic libraries, gates, flops that are provided for everybody else. So people look to me for the numbers that say, what are the problems that, random logic, we get a gate count, and so you have the random things. There's systematic errors as well, but being able to plan this thing is the key. And so you don't necessarily know exactly how your block is going to be used and what part of the system it's going to be in. So they got this wonderful concept of safety element out of context, where you don't have to know how it's going to fail and whatever, but you can just kind of think about it and come up with a few scenarios. And that in the document as it goes up, because this document travels all the way up. So let's say you're doing a block. One block, it's a communication block or something. That's used by the guy that's doing the chip. The chip has to have an overall fit rate. The chip goes into a board. The board has an overall fit rate. The board goes into a system. And the guy at the end who has to talk to the people in Detroit, or the people in Tokyo, in Nagoya, or the people in Munich or Stuttgart, hey, when's the system going to fail? Give me the data that shows that. So it goes all the way back down into here with safety considerations for A, B, C, and D. And what is the single point failure? How can one thing go wrong? Or what usually happens, and again, most of the bad things that have happened to me, there's usually been a couple things going wrong at the same time. This was going wrong, and plus I didn't have. And so there's a whole great discipline for being able to come through with this. And so you would have your standard hardware design flow. So you have a core architecture, you got your spec, and again, the spec can't wander, because again, wandering specs have all sorts of issues that come up. you can come up with a systematic failure-based verification. To go through, you can build it on FPGA, you can put your methodologies in place, and each module has to go up. Each module has a failure rate, a fit rate that gets rolled up, and it's not only through the hardware, but it's between the functional code and being able to go up through digital, and then can come up through here and verify it either as a FPGA or an ASIC. Now, with full readiness, you have your safety plan up there. This is the plan. This is how we figure out the severity of what's going to happen bad if there's a failure. There's requirements, there's goals, and there's fit rate analysis. Failure in time. And so for time is a big thing for cars. They're going to be on the road 15, 20 years. And there is a time for this to failure. And there would be hardware safety features. And there's a number of features, we'll get into those, that can be used to prevent bad things from happening. But we have this document, and again, the FMEDA has the goals on there. There's coverage metrics, fault metrics, just as you would do fault thing. And then there's various certitude. So what is the confidence level? And there's a whole branch of math that goes through, and we'll be able to figure out that one particular confidence level with a probability, and you can exchange that. And so the safety manager gets trained in that, and everyone else has to respect that particular math. And you come out, and you have your safety manual and your report, and that goes upstream to the next guy. So that's the practice. Now, what are the features of doing it? So what are you going to do as a designer to be able to do that? Hardware redundancy. Always a good thing. If you remember the early space shuttle, the Space Shuttle Challenger, they had 3 computers that were all running the same program, all attached to the same sensors. And if and so they had a voting logic that would say, I'm going to do what 2 of them say. That's redundancy. I don't think you want to do that, especially in cars. The memory in those things was iron core, if any of you remember. Maybe one of you might remember that. Before my time, too. Configuration register. Are the registers configured properly? Which is very key before you start, before you even start going. Data correction on memories, as well as timeout monitoring. Because a lot of times timeout is absolutely key. How many people have driven down the freeway for 10 miles with somebody with his blinker on? You need timeout on these things, because a lot of things, once they're started, they need to stop. Self-test. When you start up the car, you have to run a full hardware diagnostics before you start rolling. Now, again, a lot of the cars now, there's full interlock. You won't go until you go through and press the confirm and that you're running along. And so you need to be able to run that. Or if it does, it says, I'm not going to go. You don't have your seatbelt on. I'm not going to go. And so there's a self-test in there. We got hardware, timeout monitoring, frame counters, information, and even the good old standby parity. Word parity, it might be in the memory. All it does is says something broke. You don't know what, it can't fix it. And so for protection mechanisms that we have implemented is, protection on the APV bus. A bus is a good place to find faults. So you put a sensor on the bus. You have a right pointer to a buffer. So if that buffer is going to run off the end, memory protection will be able to take that. EDC protection on the header, parity on the data path. Yeah, you have to put an extra bit in there, but that is one additional safety mechanism that can be there on a CPU. Parity protection for configuration. ECC, read right into the memories. Memories are a great place for failures. The bit cell, it's a rule-stealing bit cell typically. It's the smallest set of dimensions, and there's a whole set of design rules that the bit cells have to follow that nobody else. They break all the rules, and so that's a great place. And so with something very simple as on a 16-bit word, you can put a 5-bit Hamming code on there. It detects 2, corrects 1. It's a great great mechanism to correct things. And again, replication. Go back to the shuttle there. Duplicate key modules and compare the outputs. We have triplicate word count register with voting logic. So again, we make flip-flops, and so what you do is you put 3 flip-flops in a majority gate, and if there's ever and so it always goes that way, and it also detects. It says, hey, you're there's a difference there. There's a disagreement between your computing. Let's not do anything stupid. So we're not going to do any lane switching or automatic braking, but we are going to put the idiot light on and tell you do have a problem. Drive carefully. And then there's all sorts of other ways of looking signal pulses, one hot state machine. And again, this has to be added into the IP before the IP is made. These are not the kind of things that you can add later. You can, it's more expensive. So an example of this, we have an EM safety island. This is something that we do with our 32-bit ARC core. So you'll have your main core here, MCU. You have this EM core. It's a shadow core. It executes every instruction that the other one has access to the same system bus. And safety monitor basically says, are these guys going to disagree? These guys disagree. Let's stop. Let's be safe. Let's rather than sorry. And so we have these same kind of watchdog timers, memory protection unit. This is something that's already done, and it's gone through that certification process where all the paperwork is in there, which is the hard part, and it's been certified by a bunch of people who do nothing but certify safety things. I'm not going to. We love them dearly. Okay, let's leave it there. So we have the safety features. This is what's in there to keep it safe. We talked about the practices. Now, reliability and quality is different than safety. So we covered safety, and this ISO 26262 covers that. They have different levels. There's a whole certification program, and it's only about safety. Now, what we want to do is we want to increase the reliability. To risk and development, and the American Automotive AEC has a qualification that they've been doing for years that's now going through various complete revisions that are going through, because it used to be something simple. Oh, does it pass ESD? Do they do shake and bake? Okay, it's good. Looking for lead balls inside the die. We've come a long way since then. Whole lot of other things. And then quality. Quality is something that is a process. It is in the DNA of a design team. It has to be dedicated to quality from the beginning. It has to be built in. It has to be part of the culture in order for that to be able to be really effective. And so we'll talk about these two. So, automotive reliability. Here's your typical consumer component. Parts per million over here, over time, out to 20 years. So when we go over here, how many people have had their cell phone for more than 3 years? 2 years. Not many, okay? So you can have less reliable technology. It has to pass the butter test, but not as important. Over here, you have a safe launch, long life, and here is where you sell the car. You don't want to, this is the time when one thing breaks, then the next thing breaks, then the next thing breaks, and you say, I should have sold that about a year ago, if anybody's been there. So this is the natural flow of everything, even people. I'm starting to hit that little slump myself. And so what you have to do is say, over what type of a mission profile. And so what you do is, if you go through typical silicon from some of our good foundries over here, they'll say, okay, 110, 10, at VDD, at, on the silicon would run at that point. And that's the aging of the silicon. That's what you have to design EM for. Real life doesn't work that way. So this is a typical industry example of a profile where 1,000 hours at this temperature, 2,000, 7,000 here, and at these extreme temperatures, you have less much, which simulates the life of a car. Your car is not running continuously. People say, oh, okay, yeah, I want to see, 20 years at 150C. Your car is, if you have your car like that, it's not going to last 20 years. I mean, taxi cabs in New York, 3 years is about as long as you can run them. And I think that's mostly the potholes. I don't think it has to do with the temperature. But you have to go through that and have a mission profile. So once we have that, we have an internal reference that we have for automotive grade 2 and 1 and 0 that will define the profile. And so once we have that, you would run the silicon at that old, because as silicon gets older, electromigration gets worse. It doubles every 10 degrees C, and so a hot engine doesn't really help the EM. And not only that, but as silicon ages, it gets old. Hot carrier effect, PTBI, NBTI, TDDB, all of the bad things that happen to silicon make it slow down. Leakage gets a little better, but it's not not too much of a consolation. And so the SoCs need that. So it has to be able to pass that. Now, again, a lot of this is on the end device. So the end SoC needs to run through all of this. But in order to make sure that the IP is not going to fail, and that's the cause to have to go through one of these full tests, these are expensive. You got to do 3 lots of 800, 1,000 hours in an oven running, and you have to monitor the results a half a dozen times. These are expensive. And so what you want to do is make sure the IP is not going to be the cause of that failure. And so by running all of these things in simulation and doing some testing as well, you can anticipate what's going to happen when you do run the full testing. So, and again, the different tests are important. So ESD is really important for DDR, but in the in the nice core world of embedded memories and logic, we don't have to worry about that. And for each of our IPs, there's a report that comes out. It's a reliability report that goes through how the testing was done through simulation, and whatever live testing is all done is included for each one of these particular interfaces. And so what you have to do is be able to roll up this into the conditional probability of the whole SoC. So if you have one USB, the probability of failure is X. You got 4 USBs on there, probability of failure goes up by 4. And if you have 10 million flops, that's going to go up there. So the math has to be there. So in order to show it, now again, a press release, you can, a few $100 you can put one there. But this basically shows that one of our key partners, TSMC, stands behind us in being able to commit to the program that they have. TSMC has been doing some wonderful work of taking their regular commercial IP and also running it through full tests, giving us the important data that we need in order to measure electromigration, aging, and all of the key parameters on a per layer basis of what is going to help us to be able to make quality silicon. So we can be designed for 1 part per million, 1 defective part per million at 150C junction temperature for grade 1. High reliability in automotive with foundation IP so that you can do that, and we're building it out at 16 FFC and 28 HPC plus. And if we need to go through that in-house testing, we can do that. It's a real pain. If anybody who's ever done that, it's a real pain, but we can do that. Moving on to quality, what we want to do is, it's different than safety, it's different than reliability. Now we're talking quality. And you need all 3 to make it work. First of all, what are the requirements? Is there a clear definition of what it is? And is there a plan? Does everybody sign off on that plan? Or one group over there says, no, we don't believe in the plan? we have to propel, countermeasures, have to go through and implement it. Implement the process controls. Revision controls are the big thing. And collect test data, standardize the procedures, and go through continuous improvement. In terms of the process controls, there have to be controls. You're getting ready for a tape out, and there's an open. You just have to go into your editor, put a little piece of wire there, and the problem's fixed, right? Next route, there's a revision. Somebody else has to do that. They don't know that that wire got there. So there has to be strict abilities in the release of these to make sure people don't do that, because that's how it happens. And you need a quality management. That has to be supported by management as well as have buy-in for all the team. One of the other key parts on the quality side are the DF failure measurement reports. And so what these do, they're compliance, dashboard, and repository. What these reports say, what can possibly go wrong? What is the probability of that going to happen? How many of them are on there, which increases the probability? And again, being the guy responsible for flops and gates, you have, you talk about a flop failure, you have, 100 million flops on on one of these big designs, your fit rate goes down the tubes real quickly. And have audits. And the internal audits, they're a little bit less severe, but again, if you're in the automotive business, these people are real, they have teeth, and they do audits, and they're serious. And fortunately for us, we can be grateful that they are serious in doing that. It keeps us safe. Here's a DFME spreadsheet. So what you would have is, what's the function to be analyzed? How could it potentially fail in every which way? What are the state of effects that would happen? How can you identify, detect that there is going to be an issue? And then, and how can you correct it? And the thing is, what's the risk priority? Is it going to be very dangerous for human life? And that's at the end of the day, you get into an accident, it's only metal, that's okay. But this is talking about real human life and those that we love. So to do this, we have a portfolio for automotive. We have all of these titles that are over here for interface IP. We have non-volatile memory. I won't go into all of these. Security, encryption, decryption, root of trust. This is key to be able to. Anybody could go along. Now that a car is nothing more than a rolling hotspot, hacking into a Wi-Fi network is pretty easy when the password is 1234, my car, or John's car, whatever that is. We have some very interesting stuff there. The star memory system is able to detect memory faults and various faults, especially in the leading edge nodes for such things as fin failure, partial fin failure, which is a whole new failure set of mechanisms. Embedded memories, the part where I spend all my life in logic libraries and coming up with gates and flops and being able to go through things is to measure the alpha particles and neutrons that can flip the state of a flop, and when you got so many of them, but do you really want to use the soft error rate resistant flops? They're only 2 to 4 times bigger than the regular ones. And so your PPA goes down the tubes there. Sensor control systems and data central. And again, for compliance, there's a pathway to there. And so you can see here which has been already gone through the ASIL D, the highest level of safety requirement. All of these have safety manuals that are there, as well as a certificate by this group of folks over in Germany who have found a wonderful niche for themselves. Some of these are ASIL B. Again, that's good enough typically for grade 2. And then for some of these others, we have compliance in product, it's in planned or it's in passing. It does take a while to get through the full certification. And so we have a strong commitment to safety. So in summary, we're talking about ADAS, driver assistant. Again, we saw before with the market data, it has a compound annual growth rate of 25%. A lot of silicon is going to be going into this, and those are opportunities for people to design these chips. We provide these safety features, and they're integrated into our automotive IP portfolio. For when we first got our IP, we started adding these features, and now it's part of being built in right from the beginning. When you're going to start a new IP, okay, what's your automotive plan that goes in with that? Very strong in the interface, DDR, MIPI, MIPS, HDDI, PCI. Then the foundation IP, memories, logic libraries, and test. The full analog, and our NVM has been used for many years, not only in grade 2, the infotainment, grade 1, the ADAS and steering control, but also grade 0, engine control, the stuff under the hood that has to go to 175C. Silicon does not like to be at 175C. Bad things happen. But again, for non-volatile, a lot of this stuff has to be stored. We have the processors with the safety island, safety enhancement packages, sensor control systems, prototyping kits. So the prototyping kits allow you to be able to start the design of something, pick up a prototyping kit which gives a board that with an attachment so people can start developing software while you're developing the hardware. Just so you are off the critical path. Nobody wants to be on the critical path. Let's move it to the software folks. And again, all ready for 26262, AEC verified for testing, and procedures in place for automotive quality. And so we'd like to invite you to come join us. We have a booth all the way next door, and to be able to speak with any of us on that.
Thank you, Ken Brock from Synopsys. Thank you so
very
much.